Well, first of all, I'd, of course, like to thank the Nobel Committee for inviting me here. And I have to say, I think both Serge and I agree that it's a wonderful honor, but it wouldn't have happened without many great colleagues and also the work of people in many other labs. You'll hear this a little bit the same story again. This is my version of kind of the Schrodinger cat. So, I always had great admiration for someone like Schrodinger, who, of course, was one of the inventors of quantum mechanics, but at the same time, he was willing to think ahead, and he was dissatisfied with the theory. And the reason basically is that if you take quantum mechanics alone, both Serge and I and others are used to thinking about very small systems, single atoms, single photons. But the theory should apply to very large systems, and early on Schrodinger realized that, and to explain the problem he had, he posed this example where a cat and a radioactive particle were in a sealed box, so that it was a closed system, we say. And in any case, his example, if the particle decayed, it would trigger a mechanism that would release poison and kill the cat. Well, in fact, of course, we can't write down the equations of motion for the system, but it'd be too difficult. But in principle, we can. And basically, all quantum mechanics tells us is that after a time equal to the so-called half-life of the particle, all we can say is that from quantum mechanics is that the state of the system is where the particle has not decayed and the cat is alive, and not but the particle has decayed and the cat is dead. And we represent this mathematically with these symbols here, but the key thing is that all we can say is that the cat is neither dead nor alive, it's both. So that was, of course, what bothered Schrodinger. Now, one thing, this idea of superposition, which the Schrodinger cat is a good example of, I think. I like this example. Chris Monroe found this book when he was in our group, and anyway, I think it's a really nice example. You can think of, if you think about this box up here, and if you, of course, play with your eyes, you can either see this surface here be in the foreground, or the surface on the upper right be in the foreground. And so you tend to see either this surface in the foreground or that surface in the foreground. And I think it's a useful analogy, because in this picture here, it basically has both properties. And this is what we call superposition in quantum mechanics. There's some ambiguity about which state the box is in, and it actually possesses both properties simultaneously. The other thing is that when we talk about doing measurements on quantum systems, it's called collapse or measurement projection. And this example also shows that, I think, in a nice way, because when you look at this box here, and for example, at an instant, you might see this surface be in the foreground, like this picture here. That's very much like measurement in quantum mechanics, even though in the superposition state, the box has both properties. When we measure it, one feature will come out, and that's very much like measurements in quantum mechanics. And then we talk about entanglement in our system, and so if you'll at least open to suggestion here, the idea is if you have two boxes like this, at least for me, I tend to see, if I see this surface be in the foreground, like down here, I tend to see the other surface also be in the foreground. And so when we measure these entangled systems, there's a correlation. So in this example here, if we measure this surface to be in the foreground, then we tend to see this surface also be in in the foreground. And so this analogy kind of explains this idea of this entangled superposition. And just coming back briefly to Schrodinger's the cat, if we, to show the entanglement, we call this an entangled state where we have this correlation of the particle not decayed and the cat alive, and the particle decayed and the cat dead. And those if we see the particle when we do the measurement undecayed, then the cat is alive, and so on. So, well, anyway, of course, as I say, Schrodinger was bothered by this consequence of the theory. And he really struggled with this, throughout his career. And so at one point he, maybe out of frustration, he said, well, look, we cook up these situations with simple systems like atoms, but maybe that leads us down the wrong path. And the way he said this is that, so one way out of that, according to him, was that, we can cook up these so-called thought experiments, but that's going to lead to trouble, and in fact, we can never deal with single atoms or molecules, and it leads to these ridiculous consequences like Schrodinger's cat. Well, in fact, we now know that we can enter this world, but so far we can only do it on very small systems. But nevertheless, I'll try to show you that they have all the features of Schrodinger's cat. And to get to this point, what we need is, first of all, we need precise control of these systems, and lasers and computers and so on have helped us to do that. We also need to isolate our small, simple systems from the environment so that these superpositions aren't disturbed. And so the target is here to, at least to start to see some of these effects, is the precise control and being able to control small numbers of particles. So I'm going to take a sort of a personal view through this. I think basically what's nice for me in the way the citation read for the award is that basically everything in my career led up to the kind of things we're doing now. So it'll be a little bit of a personal story, but of course, again, it's many other people involved in this kind of work over the years. So this is a picture of Norman Ramsey's group. I was a graduate student in Ramsey's group. At the time, he and Dan Kleppner developed the hydrogen maser, and many of you know that Norman here was later part of the citation for his Nobel Prize was this development of the hydrogen maser. So that's me there trying to get close to the boss. So my thesis was to make a deuterium maser to measure its hyperfine frequency. And one thing I always muse over is the fact that I'm probably the only person in the universe that has that number memorized. So anyway, that was a result of my thesis. But anyway, this was good training in the sense that to get these high precisions in these frequency measurements, we have to have very good control over the system's environment, in this case, the hydrogen maser. Also this, I won't go much into this, but when the atoms are radiating, they're in a superposition state between the ground and excited state, and these atoms in the maser would live on the order of the superpositions of the atoms in this deuterium maser would last about a second. This was not at the single particle level. This was on an ensemble of atoms that were inside the microwave cavity. So after getting my degree, I went on to work with Hans Dehmelt, and although he was interested also in atoms, and in this case charged atoms, the focus of his work then was to do experiments on electrons. And during the time I was there, we developed techniques to look at single electrons. So a good picture to have, I schematically show an electrode structure here that holds the electrons, and you can think about them oscillating back and forth. And a good analogy for that system is you can think about a marble in a bowl that the marble rolls back and forth. Another analogy which some of you may get is that if we can think about this system, this charged electron, and inside of this electrode structure, it's mimicked by a so-called tuned circuit, an inductor and a capacitor in series. And if we stick this, then this equivalent circuit into a simple electronic system where if we drive the tuned circuit on resonance, we'll get a current through a resistor which we can read out. And the reason that was interesting to help to try to find or at least isolate single electrons in this experiment is that we could basically drive the oscillations in this equivalent circuit, or this amplitude of the marble in the bowl. And in this experiment here, what we did is we started out with 7 electrons in our atomic bowl, and we drove it just at an amplitude where occasionally one of the electrons would fly out of the bowl, go over the edge, and we'd see this step process in time. And so we'd see the individual electrons leave, and we got down to this last step here that identified a single electron, and then we could go on and do measurements on this single electron. And very briefly then, of course, Hans Demolt and his later colleagues went on to do an accurate measurement of the magnetic moment of a single electron, and in fact this led to Demolt's Nobel Prize, that is this precise measurement of the magnetic moment of the electron. So at the same time, we were also thinking about ideas about how atomic ions might be used for clocks, coming back to my graduate school work. And there was one of the things we would like to do is to reduce the temperature of the atoms, in our case the ions, and so we had some ideas about laser cooling, and at the same time also Ted Hinch and Art Shallow had some similar ideas. They didn't look so similar in these brief write-ups, but they're in fact very closely related. Anyway, after my postdoc work with Hans Demolt, I went to National Bureau of Standards, which is now called NIST, the National Institute of Standards and Technology. So my first task was to help get the atomic beam machine, the cesium beam frequency standard going. Fortunately at that time, my boss, the fellow that hired me, Helmut Helvig, at that time NIST or NBS was pretty much of a service organization, at least the part that did the frequency standards. And so Helmut was very instrumental. He kind of beat on the administration to get us some money to start experiments, first to do the laser cooling, and then from then on apply that to atomic clocks. And so that was really the start of this business in my career at NBS. And anyway, so we did some experiments, and at the same time, Peter Toshek's groups was doing some experiments, and actually Hans Demolt joined them on this. And what's kind of interesting, you'll notice that the dates of publication are very close together. We were a little earlier than our paper was published a little earlier than that of Peter Toshek's group, but to be fair, you see that they actually submitted their paper a day early, so I guess you'd have to say they were the first. So one thing that was interesting about this is I think I knew because that they were working on this because I knew Hans Demolt had gone to spend a sabbatical in that group. I don't think they knew we were working on it, so it was really kind of an amazing coincidence that this work was submitted within a day of each other. Anyway, in the experiment in Peter Toshek's group, the evidence for cooling was that they were able to hold the ions into the trap a much longer time. Based on the techniques I had learned, I told you about the induced currents that we could measure of electrons. In this case, we just looked at the thermal currents of the ions in the trap, and we could, if we turned the laser on, we could see the temperature go down, which was just a measure of these measured by these induced currents. And we could see the cooling effect in that way. So this was our group in 79, not very long after these first laser cooling measurements. And the embarrassing part, I think, at least for me, is I can see I aged a little bit. I must admit, both Wayne Itano, who's here, and Jim Berquist haven't, they don't look much different, but I think Bob Drollinger over here, who's also here, we suffered from the ravages of time, I would say. So anyway, moving on, one of the goals was certainly at NBS NIST was to try to apply these cooled ions for frequency standards. The reason that's important is that we want to reduce what are called Doppler shifts, and one of the more interesting Doppler shifts is the so-called time dilation shift. This comes from Einstein's theory of relativity. If the ions are moving inside this trap, we call it, then time runs slower for them. This is the basis of Einstein's twins paradox. And so the laser cooling would be very important for that, to reduce this rate of time shift. And so that was the importance there. But nevertheless, we also wanted to think about getting the number of atoms we were using in the clock to very small numbers. And the reason for that is just that we can control the environment much better for single atoms or ions than we can for a large ensemble. So what this shows here, that actually the first experiments isolating single ions were these experiments also again in Peter Toshek's group. And they actually made some pictures of single barium ion in this case. Our work was a little bit later. We also went back to the same idea that I showed you with electrons. In this case, we kicked magnesium ions out one at a time by using a chemical charge exchange process. But we could identify the ions at the single ion level. You see here the last step in this picture indicated when we had a single ion. So anyway, we have carried on with these experiments after that, and the idea, again, and this is in the context of clocks, one of our favorite choices was mercury. It had two transitions, one in the microwave region and also one in the optical region that might potentially be used for clocks. So schematically what we had is this electrode structure, this kind of donut-shaped things, and some other things down here we call end caps. Anyway, the idea was that if what I show here is an energy diagram, and if we tune a laser beam such that this radiation connects this lower level to this excited level, then the atoms can scatter photons. And if we tune, the laser cooling process relies on tuning this laser slightly below the resonance frequency of this transition. The thing that made this hard was that this wavelength was in the ultraviolet, and certainly this is where Jim Berquist was key to this work, because he's the laser expert and continues to be the laser expert in our group. So the idea of a clock, the way we could make a clock on this, there's another transition in mercury, and this one has the feature that it has a much narrower range of frequencies over which it absorbs, and so we can get higher precision on the frequency of the laser when we make this transition. One interesting thing is that we can use this transition that we use for the cooling to detect when this transition is made, because if the ion is promoted from this ground level up here to this particular excited level, then the scattering on this on this laser cooling transition will be diminished. And we can tell then when we make the transition with the laser tuned to the so-called clock transition. At this time, there was a bit of controversy among the theorists about whether, if we did this experiment, that is, if we tuned this laser and hit this resonance transition, would this scattered light just diminish sort of smoothly, or would the atom sort of jump from one state to the other? That is, would it be either here or here? And in fact, the atom does jump when, as indicated by jumps in this scattering. So if we promote the atom up here, then the light just completely shuts off rather than be just diminished. And these, again, the same people. This was now Demoult's group and Peter Toshek's group and our group that did some experiments on this about the same time. So I have to, we have much fancier versions of these things now, but this will give you an idea of a little movie we made in '86 showing these jumps. So this shows this same kind of electrode structure. This is the donut here, and the pictures get poorer in quality here. The first, that was the trap just mounted on a penny. This is now looking through a window of a vacuum system, but you can still make out the ring, the donut-shaped structure in the so-called end cap. And then this picture is taken with an ultraviolet camera, whose quality is pretty poor. You can still see the outline of the donut, the inner part of the donut here. And as the movie goes on, you can start to see the scattered light from, in this case, this single mercury ion. And what we're doing here is we're tuning the cooling laser closer into resonance so the atom will scatter more and more photons. But while it's changing state, you can start to clearly see the atom blinking on and off. And when it's not scattering, that means it's in that upper right-hand level. And you can clearly see these so-called quantum jumps. So from this work, we wanted to go farther. This was a way to detect the quantum levels, of course, that were affected by the lasers, but we also wanted to control much finer level the levels of motion of the ion in the trap. So if you expand this black line here, basically the classical picture again of the ion in the trap is this marble in the bowl, but in the quantum picture, what we need to think about are the energy levels, the ground energy level when the atom is closest to rest that we can get it, going on up with so-called excited states and of the quantized motion. Now the gap between the ground and the first excited state of the motion is about 8 orders of magnitude, about 100 million times smaller than the gap for the energy of the photons that are driving the laser transition. So we had, of course, had to have much better control to be able to control down to the quantum levels of the motion. So what this picture shows is if we tune this laser such that when we drive this so-called electronic transition, if we tune the frequency of the laser so that the motional energy state doesn't change, then we can see a feature here. What this shows is the probability of seeing fluorescence, and of course when we hit the transition, then the probability of seeing the scattered light goes down, and which is why you see these dips here. Well, we can also tune the laser so that if we start in this, say this n = 2 level, we can change the electronic level and also increase the motional quantum level by 1, which is indicated by that feature there. We can also do the other side, and if we go drive the electronic transition and also decrease the motional state by 1, that's indicated by that picture there. So anyway, we could start to see these kind of quantum features in the motion. And one interesting thing, we could use this so-called, these sideband features to do a further kind of cooling. In this case, first of all, the conditions were such that if after the atom was excited to this upper manifold of states, when it decayed, the conditions were such that it would decay back down without changing its quantum number. So the idea of this further cooling was that we would excite on this so-called red sideband, the lower frequency transition. So if we started here, we would decrease the motional quantum number by 1, then we would let the atom decay, and we would repeat this process so that if we excited then there, it would eventually come down to that level. And the interesting thing, of course, is that when we get down to this lower level, then there's no excited energy level, motional energy level for the atom to go to, so the scattering stops. And that was then an indication. What you're seeing on this right-hand picture, this feature here collapses down into this feature here, and similarly this one represents one here. And you can see a big asymmetry now in these features, and the fact that this so-called red sideband is disappearing means we're predominantly in this situation here where we don't get any absorption, and the atom then indicates the atom's in its ground motional state as well. Well, anyway, let me just come back a little bit to the clocks. We got with the cooling and trapping, laser cooling and trapping, we could reduce these Doppler shifts, and taking some other care to reduce other perturbations to the system. Jim Berquist is the main person that has led this work, and this really started in 1981, and his experiments on mercury were actually the first clocks to exceed the performance of the cesium beam frequency standards. And nowadays we all think about optical clocks rather than microwave clocks in terms of high performance. Anyway, so around 1995, these ideas of quantum information processing, more commonly referred to as quantum computing, came around. There were some early ideas by people like Richard Feynman and others, but they were just kind of toy ideas, I would say. And then what really set the field off was that Peter Shor, a computer theorist, came up with an algorithm that said if you could make this quantum computer, you could efficiently factorize large numbers. The reason that's important is that if we could accomplish this task on very large numbers, that would have very important implications for encryption and secret coding, basically. Anyway, not long after Peter Shor described his algorithm, actually Art de Record, who was already an accomplished person in doing quantum communication, came and gave us a lecture to the atomic physicists on this, presenting these ideas of quantum computation. And fortunately, both Peter Zoller, who's in the audience, and his protege at that time, Ignacio Chirac, they quickly jumped onto this idea of quantum computing, and they came up really with the first scheme for how you might build a quantum computer, and it was based on ions. So the idea is here, this picture is just to represent some sort of electrode structure. You can still think of the marbles in a bowl in some sense. In this case, it's kind of a linear bowl where the ions all want to fall to the bottom of the bowl, but the Coulomb repulsion, due to their charge, holds them apart. Anyway, their idea was that in this example of 5 ions, it's kind of like a pseudo-molecule. You can think about the normal modes, the vibrations of the molecule, and they all have different frequencies in general. So you can think about the ground and first excited state of one of these modes of motion of the molecule. Also, as what we call a quantum bit. In other words, a two-state system that can represent information. And their idea was that you would use the internal states of ions. They could be either optical states, like I showed with the clocks, or hyperfine states. In principle, it doesn't matter. Anyway, their idea was to be able to make quantum gates if we could, with a laser beam, if we could somehow map this superposition state onto this motional state, then we would this motional state is interesting because it's shared with all the ions. All the ions share one motional mode. And then to make a gate then between the two ions, you'd first do this mapping step, and then on a second selected ion, you'd do a quantum gate between the motional mode and the internal state of this ion, which would then basically have made a gate between the first selected ion and the second selected ion. So I won't give you details of exactly how this works, but I give you kind of a sense of how logic gates work. So if we have this, in this case it might be an optical transition, and if we isolate these two lower motional quantum levels, which also represent a quantum bit, then one way you can kind of get the idea of how logic gate works is if we, I have a truth table down here, and the idea is that if this bit representing the motion is called if we refer to that as the control bit, and this is the so-called target bit, then the idea is if we tune to this transition where we reduce the quantum number by 1, then the idea is if the control bit is in the n equal 1 level, we can do this transition. In other words, we flip the bit of the target bit. If it's in the ground state, again, there's no place for this to go, so the target bit doesn't flip. So we get this kind of logic table. And this was a little too simple, but it gives the essence of the idea, this logic gate. Anyway, so Chris Monroe, who was in the group at that time, we were kind of poised to do this, so we could jump on this idea right away, and we were able to demonstrate a more general logic gate that both Ignacio and Peter had described. The one thing I want to say is that for both Peter and Ignacio is that this really stimulated the ion trap field, and this is by my last count, the number of the people working on just quantum information related experiments with ions, and of course there's many other possible implementations of quantum information, and so this. But anyway, both Peter and Ignacio have gone on to stimulate a lot of work in other areas as well. So let's see, I didn't give myself enough time here, but let me give another version of Schrodinger's cat. So you think about this marble in the bowl. What we can do is that we can first start the atom in its ground internal state. We can then apply radiation to make a so-called superposition of the ground and excited state. Then what we can do is that using so-called optical dipole forces, we can apply a force to the atom, but it's a force which only acts on the upper state, not the lower state. So we can start to separate this superposition both as well as in terms of what we call the spin, represented by the arrows, but also the position. So we can apply a beam that starts to push the up component, and it's oscillating back and forth, and then we can flip the spins, and then we apply the same force again, but we can apply it with a little bit different phase, and we can realize the situation then where a marble is at some instance of time, it's both on the left side of the bowl and right side of the bowl, correlated with the direction of the spin, in other words, the internal energy state. And we would say this is very much like Schrodinger's cat, in that we have a more classical-like property, the separation of the marbles or the positions of these states in the bowl correlated with a microscopic property, that is the internal state of the atom. So this is a picture of the trap we used. And this, very much like what Serge said, we can't make a very big cat in this sense. In fact, the wave packet size of the, in this case, beryllium ion, we could make the cat state be such that it was about 8 times the size of the wave packet, which is still very small. And in fact, after this paper was written, we got a comment, there was a comment in letters to the editor, and we called a Schroedinger kitten, but this fellow, Andrew Algren, said that, well, even that's too big to call it anything like a Schrodinger cat. And so he says, call it a Schrodinger furball. And I think that what I took from this was, I think this is interesting because I think it does have all the same features as Schrodinger's cat. And if it's not big enough, how do you define big? And I think none of us know how to define big. That is, where does the classical behavior overtake this quantum behavior? And I think none of us know the answer to that. So let me just say briefly that this subject goes on in a big way now. There's many people working on it. Certainly in our lab, Didi Leibfried led a lot of the early algorithm demonstrations and continues to do that. One of the things I think most physicists are looking forward to is the idea that these simpler systems, forget factoring big numbers for a minute, just even small numbers of particles may be able to simulate other systems of interest. And one thing that several groups are thinking of is I talked about these oscillations of the marbles in the bowl, and you can think of those as oscillating dipoles. Those can mimic magnetic spins in a solid, and so this is a picture of John Bollinger's experiment where he has an array of ions in a hexagonal structure, and this can simulate some interesting spin systems in condensed matter. And certainly at the moment, the best performing quantum computer, you might say, is that of Rainer Blatt's group in Innsbruck, and they're able to actually, at least on a small scale, make a real quantum computer. So far, we can simulate this quantum computer on a classical computer, but I think we're all feeling now we're getting to this threshold where we're going to get to systems that we can't simulate on a normal computer anymore. That is, we're really going to be able to use this quantum computer. And of course, there's many, many more people working on this, as I indicated. Since I know I'm running long, let me just say briefly, we've gone on to use some of these ideas, these simple quantum information ideas in our clocks. And I regret that I won't have time to give full credit, but in our lab, Till Rosenband leads a project using aluminum ions as a clock, and I won't go through all my punchlines here except to say that now this clock that Till Rosenband has developed is the world's most accurate clock in the sense of getting rid of these environmental perturbations. And in fact, we can see some interesting gravitational shifts in the clock. And this, oh heck, I'll have to indulge you and ask your indulgence. And we have a little cheesy movie here which shows this was one of the aluminum clocks on this optical table. And James Chow here raising it up on a jack. And when we did this, we could measure the so-called gravitational redshift, gravitational potential redshift in this experiment. And by raising the table about 33 centimeters, we would predict a shift like this, and we measured, at least within the air, or something like this. And this may lead to a new kind of way to measure, to do geodesy, and we're looking towards that. So let me I will stop now. Sorry about that. Anyway, I do want to, again, I think, want to thank my local colleagues, John Bollinger, Jim Berquist, and Bob Drollinger, and Wayne Atano, and I have been together around 30 to 35 years, and we're still working together. And more recently, Dee Dee Leibfried and Till Rosenben have joined us, and Chris Monroe was really instrumental in these experiments that I briefly described. And of course, it's really hard to give proper credit, but we've had over 100 students, postdocs, and visitors over the year, and certainly we've enjoyed really good support from our bosses. And particularly, I want to acknowledge Catherine Gebbe, who's the head of the lab. She's my boss's boss, and she's been very supportive of this kind of work. And I think certainly her success is maybe partly measured by me, but also Bill Phillips and Eric Cornell, Jan Hall, who also received Nobel Prizes. She has been the lab director during that time. And finally, of course, it's been a nice, have nice friends along the way, and including Claudine and Serge. This is my wife, Sedna, and we've certainly enjoyed their friendship over the years. And sorry to go so long, but thank you.
Okay.